Okay, in this lecture, we will begin a discussion of the last topic for this course, which is normalization. And it really has to do with developing the structure of a relational database. And it's a formal and rigorous method of doing something that we did informally right at the beginning of the course. Okay. So, to set the stage and to give us a launching point for a discussion of normalization, let's go back and for a few minutes revisit and remind ourselves of something that we did early on in the course, in fact, in the very first lesson, that has to do with database structure. Okay, so you may recall that we started off by saying that it is important to structure your data in a proper way, otherwise it will affect your ability to manage the database. That's what we had said informally. And just as a reference, we said, why bother with database structure? Why not put everything into one big table? And that's where we started. So this was a sample, simplified, one big table that we had started off with. And we very quickly realized that putting all your data into one big table causes problems. And if you recall, three specific problems that we identified were things called insert anomaly, update anomaly, and delete anomaly. So just through that quick discussion and that in that very first class, we came to the conclusion that putting all your data into one big table or one big relation doesn't work well. It's got its problems. So what did we do informally again to fix that problem? In that very first class, we said, well, let's find different themes that are there in this one big table. And we had come up with and identified a theme called student, and we had identified a theme called faculty. And then we had developed, we'd identified columns or attributes that can be used to connect the two. Okay, so the informal action that we had taken to address the problems arising from putting everything in one table was to find themes. But if you remember, the way we found themes and identified parent-child relationships between the themes, the process of finding the themes was relatively informal. So we sort of scanned the columns that were present in this one big table, and we asked ourselves which columns might go together, and that's how we identified the columns that constituted the entity student. And then we said, oh, there's a bunch of other columns that sort of hang together with some with faculty, and that's how we identified the second theme. And then we said, oh, by the way, if we split this one table into two themes, we lose the connection between the two, and then we had to find some column that would connect one with the other. So this structure, this very simple, starting from a one table and splitting it into two tables, that is sort of the initial baby steps towards creating database structure. And this was the discussion that we had to motivate the next few lectures, where we looked into ways the data modeling process that you actually went through to go ahead and design the structure of the database. Okay, so this theme splitting process that we saw informally at the in the very first class, you will see soon enough that normalization is a rigorous way. We identified the themes informally, but through normalization, once we learn what normalization is, how it is done, you will find that it provides a rigorous way to examine a table and come to a conclusion. Is the table good? Good meaning, does it have any of those anomalies? And if it is not good, the normalization process is rigorous enough to tell us how exactly to split it up into smaller pieces, into themes. So what we did informally at the very beginning, we are about to learn a process called normalization that lets us do it much more rigorously. Okay, now prior to doing that, since this is a way of structuring a relational database, I want to revisit some concepts from relational database, the relational database model. If you remember, at the beginning of lesson 2, before we got into entity relationship modeling, since the end product at the end of that data modeling journey was a relational database, the structure of a relational database. At the beginning of lesson 2, we had gone through a discussion of the relational model, some basic concepts associated with the relational model. We said something like, we made a statement that all relations are tables, but all tables are not relations. We introduced a concept of a primary key, foreign key, and so forth. So there were various concepts, constructs that we had introduced in the context of the relational data model. Okay, so I want to revisit some of those, because normalization is a process of start looking at one of these relations and asking ourselves, is it good, is it in good shape, or do I need to break it up, do I need to do I normalize? You might informally think of it as making a table which is abnormal in certain ways, sort of cleaning it up and make it more normal in certain respects. Okay, so the discussion that we're about to have now, we haven't yet started normalization, but before we can do that, since normalization is a process associated with designing a relation and making sure that a relation is good, it has desirable properties, I just want to go back and revisit some of the concepts that we had introduced when we discussed the relational model in lesson 2. Okay. So we will revisit what constitutes a relation, what makes a relation, what are the properties of a relational table, and what are the importance of those properties. Now, we had discussed the relational model somewhat informally. I've given you the basic ideas of the model, but here now we will get into much more nitty-gritties about the properties of a relation and what's the significance of those properties of a relation. Okay. So we know that a relational is a two-dimensional table. We had said that all relations are tables, right? So a relation is a two-dimensional table that has some specific characteristics. Let's see what those characteristics are. Every row, remember when we talked about the entity relationship model, we said something called an entity class and an entity instance, okay? So if you think of this table, every row contains data about an entity instance. So in this case, the table called employee, this is a table called employee, that is the entity. Every row is an entity instance. So this is each particular employee is stored, the information about each particular employee is stored in an individual row. And the columns are the properties or the attributes of the entity that we are storing. So for every employee in this particular table, for every employee we store an employee number. There's a last name of the employee, the email address of the employee, a department, and a phone number. Okay, so at the very least, a relation is a two-dimensional table. The rows contain data about instances of the entity, and columns contain data about the properties or attributes of the entity. Okay, this is something we had already seen in lesson 2, just sort of a recap of that. So in terms of the mapping of relations to tables, the name of the relation is the name of the table. Attribute names in a relation correspond to the column names, and the identifier of a relation is the primary key. Okay, so those are the mappings between a relation. Remember when we had the ER diagram, we had relations, and corresponding to the database table, when you go to the relational schema, if you remember that journey that we took for the data modeling process, we went from the ER diagram to the relational schema. In the relational schema, we had database tables. Okay, so the relation name became the name of the table. The attributes that constitute the relation became the names of the columns, and the identifier for a relation. So the property or properties that uniquely identify an instance of an entity, that's the primary key of the table. So that was the mapping between a relation and the physical table itself that implements that particular relation. Okay. So far, so good. Everything that I've said so far is sort of a recap of things that we had said in lesson 2. And now we get into a little more specifics, a little more details about what constitutes a relation. Okay? In lesson 2, what we had said was all relations are tables, but all relations are not. But all tables are not relations. Okay? So for a table to be a relation, the column values must be atomic. Okay. all that means, we will see what we mean by atomic in just, I think intuitively you can get what the word atomic means, that the values in every cell of the table, they cannot be subdivided any further. That's what the word atomic means. So there shouldn't be composite values in any cell. Okay. Every row must be unique. There must not be any duplicate rows. Every column name must be unique in the table. The column values must be of the same kind, and they must be storing conceptually the same thing. The sequence of the rows is insignificant, and the sequence of the columns is also insignificant. So these last two properties of a relation are important. They have important consequences. We will see what those consequences are as we go along. Now, just by itself, these definitions, of the properties of a relational table may not make much sense. Hopefully, they will become more evident when we look at some specific examples. So as I said, atomic, every cell in the table, every cell must be atomic, meaning the column cannot, the value cannot be subdivided any further. This is what what we mean by atomic, a value being atomic. Okay, must be single value, it cannot be split any further. For instance, if a cell in the table contains an address that is stored in this manner, house numbers, street, city, state, zip code, everything, all of these things are in one cell, then one can reasonably argue that this value is not atomic because it can be subdivided into further pieces. But if I take any one of these by itself, let's say I take zip code by itself, zip code cannot conceptually be divided further. So zip code by itself is atomic. But if I think of address as these different things together, that is street number, street name, city, state, and zip code together, then that collection, that whole address is not atomic. So I hope you get a sense of what we mean by an atomic value and a value that is not atomic. Okay. So let's take a look at this first table. Then we're looking at a specific example. So here's a table with 3 columns. Okay. Now you can see that the names of the 3 columns are distinct. You can't have 2 columns with the same column name. That's one of the requirements. Here we are, that each column name must be unique. Okay. Now, one of the requirements of the relational model is that every relation, every cell in the relation must be atomic. So these column values are atomic. Okay. So let's see if that condition is met. So if I look at this particular table, for every employee, I have their ID number in the first column. I have the name of the employee in the second column. Note that the name is a combination of first and last name. Okay, that's how I have it now. We will argue whether it's atomic or not. And then for phone, I have 2 phone numbers. Maybe one is a work phone and the other is a home phone. So I have 2 phone numbers. Now, one can easily argue that this cell, the cell corresponding to the phone, is not atomic. There are at least 2 distinct values in here. This is not, so this table does not meet the conditions of a relation. It's a table, but it doesn't meet the condition of being a relation. Same thing, one could make the argument that name is not atomic because I can conceptually further subdivide it into first name and last name. So all in all, everything taken together, this particular table is not a relation. Okay, because it doesn't meet one of the basic properties of a relation, that is, the cells in the relation must have atomic values. So how do I address that? How do I make this table a relation then? So I break up the name into 2 columns, first name, last name, and I break up the phone number into phone 1 and phone 2. Okay, and if I know that the first number is the landline and the second number is the cell phone, then instead of saying phone 1 and phone 2, I could say landline and cell phone as the heading, as the name for the 2 columns. But the essential point here is that this value, which is not atomic, is being split up into its conceptual components, and each component is being atomic, is made into a separate column. So going from here to here, I have modified the structure of the table so that it now meets the conditions of being a relation. So I have all the columns, and there are no duplicate column names. And every cell, if I go to any one cell, it has a value that cannot be subdivided further. Okay. One could make the argument that phone number is not atomic. If we think of phone number as area code plus number, then I suppose one could further subdivide phone into area code and phone number, in which case I would need to split this column into two columns. One would be phone 1 area code, and then the second column would be phone 1 number. If I did the same thing for phone 2, I would say phone 2 area code followed by phone 2 number. Okay, so what sometimes it's pretty obvious whether a cell has an atomic value or not. Sometimes it's not so obvious. For example, whether or not this phone number is atomic is open to interpretation. Many people would say that this 10-digit number is atomic. I cannot conceptually break it down further. Okay. However, someone could also make the argument that, hey, there are really two pieces to this phone number. There's the area code and the phone number itself. Okay. Nowadays, of course, with the advent of cell phones, this first 3 digits being interpreted as an area code really is irrelevant. It doesn't refer to any geographic area anymore. So in today's world, it would perhaps make sense to argue that this phone number as a whole is atomic, that you cannot split it up any further. So I hope you got a sense of what it means for values in any cell to be atomic. So in order for a table to be a relation, one of the conditions that needs to hold is every value in that relation must be atomic. Okay. Let's see one more example and have a discussion about whether or not cells in the table have atomic values or not. So here you have a table or a relation that has 2 columns. One is a course number and one is the course name. Okay. Now, if you look at the course number, it says MIS 303, MIS 310, and I suppose one could think of this course number as atomic, but one can also make a counter argument that, look, there are 2 pieces to this course number. There is the subject code and there is the course number itself. And it may make conceptual sense to split this guy, to not think of course number as atomic, but rather that it consists of 2 separate pieces that can be conceptually broken down into two pieces. One is the subject code and the other is the course, the number, just the numeric value of the course. So the value of the benefit of breaking it up into 2 pieces over here is that you could have finance 303, you could have finance 310, okay, and be able to identify MIS courses. If I want a list of all MIS courses, then I can't think of, I can't consider these 2 together, okay. So there can be conceptual reasons to break this break this course number down further. So here we are saying that the course number, we are providing an argument for claiming that course number is not atomic, but rather it should be broken down into 2 pieces, broken down further into 2 pieces, one being the subject code and the other being the course number. I think you would agree that if we break up this one column into these 2, further into the atomic pieces, then later on down the line, if you think of the kinds of queries that could be issued to the database, if I wanted a list of all the MIS courses, if I have this structure, that would make it easier to extract that information rather than if I had the subject code and the course number together as one, considering them as an atomic value, considering this pair as an atomic value. It would make the searching process a little more involved. Okay. Now, a second property that needs to hold in order for a table to be a relation is that every row must be unique. Okay, so let's go back to those 6 the properties of a relational table. What properties does a table need to have in order to be considered a relation? The first one we said is all the column values must be atomic. Okay, so we have been having a discussion about that. The next property is that each row must be unique. Okay, so all this means is if I look at two rows in the table, they must not be identical in all the values. So at least one of the column values should be different. So here, if I have two rows in the employee table that look like this, let's say one row says employee 123, Doe, John, accounting, and this particular email address, and the same thing shows up in another record, then that is not allowed in a relation. And I think conceptually you can understand why that's the case. We just said a little while ago that every row in the table represents an instance of the entity. Okay, so two different rows are supposed to represent two different instances of the entity. If the two instances are different, they must differ in at least one property. If I claim that two instances of an entity are different, they're two different instances, it cannot be that all their properties are the same. Then they're really the same instance. Okay, so if I look across all the rows in a relation, I cannot have two rows that are absolutely identical in all the values of the columns. Okay. So here is an example where two employees, where we have two records in the table that are absolutely identical. So you look at this first record and you look at this fourth record. They are absolutely identical. What does it mean for two records to be absolutely identical? They have the same values for each column. Okay, so if I go across the 5 columns, I go across the 5 columns here, they're absolutely identical for the two records. That's not allowed for a relation. Okay. This structure is a table, it has rows and columns, but it does not, it violates the property of a relation. So what do I do to fix that? I get rid of one of the duplicates. I get rid of the one of the duplicates, and instead of, and then I'm left with John Smith as one value. Okay, so this is removed. So I'm left with these 4 rows. So duplicates have to be removed. I can't have duplicate rows in a relation. The next property that needs to hold in order for a table to be a relation is that every column name must be unique. I can't have 2 columns with the same name. And again, conceptually that makes sense. What do the columns physically represent? They represent properties of the entity that are being recorded. Okay, so if I have 2 columns, conceptually, this means these are 2 different properties of the entity about which data is being stored. So they obviously cannot have the same name. If they have the same name, that means these 2 distinct columns are recording the same property. Okay, since columns represent different properties, then they should have distinct names also. Right? So just as an example, we had an earlier example here. So in the previous example, this table has 1, 2, 3, 4, 5 columns. Okay. What I cannot do is I cannot call these last 2 columns I cannot call both of them phone. Okay, so I cannot have two columns with the same name. Perhaps the first column is a landline phone number. So instead of calling it phone 1, I could say landline. And maybe the second one is the mobile phone number. So instead of saying phone 2, I could say mobile phone. But the 2 columns cannot have the same name. Okay. So this picture shows what I have just been saying in words. That is, I cannot have a table where both these columns have the same title, have the same name. So I have to give different names. In this case, we are not being very creative. We just said phone 1 and phone 2. If I knew more about what these 2 phone numbers represent, home phone, work phone, then I could say home phone as the title for the first column, work phone for the second column, and so forth. Okay, but in any case, the names of the 2 columns must be different. I cannot have 2 columns with the same name in a relation, simply because conceptually every column represents an attribute or a property of the entity. So I can't have 2 different properties having the same name. Okay. The next condition that needs to hold for a table to be a relation is that column values are of the same kind. That is, all the values in the column are of the same kind. What does same kind means? First of all, the format must be the same. Okay. Second, and this is, I think, the more important one, is that conceptually, all the values in the column should be representing the same kind of thing. That is, remember we said a column is a property of the entity, okay? And the rows represent instances of the entity. So in each case, whatever measurement I have, whatever data value I have, if I focus my attention in one column, whatever value I have should be for conceptually the same thing that I'm measuring. Okay, so let's illustrate that with an example. Here we have a table of employees where the first column is employee number, then first name, last name, department, email, and this last column is phone. It just says phone. Okay, that's the heading for the column. And if I look at all the values in this column, all the phone numbers have the same format. So it's 7 digits long. So number, 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 dash, number, 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 number. So 3 numbers, dash followed by 4 numbers. That's the format. It's a number. And that's exactly the same format for all the values. Okay. Therefore, it meets the second condition, that all the data have the same format. All right. So if they don't have the same, if I have one phone number that is 10-digit long and I have another phone number that's 7 digits long, that's a violation of this rule. But here's a more serious issue here. For this column, all the phone numbers have the same data format. All right. So they pass the second test over here, that they must have the same format. But where is the problem? They conceptually represent different things. For these first 3 employees, the phone number represents maybe their work phone or their mobile phone. But for this 4th employee and the 6th employee, the 4th employee, this number represents their fax number. And for the last employee, this number represents their cell phone number. So even though all the numbers in this column have the same format, conceptually they don't all represent the same thing. Some of them represent a work phone, some represent a fax number, some represent a cell phone number. Okay, so they don't represent conceptually the same thing. That's a serious issue. Whatever values you have in a column, they should represent conceptually the same thing. Okay, so how do I fix that? So since I have, let's say this is a landline, and I have a fax and I have a cell, I create 3 separate columns. Okay, and whenever, if a number happens to be a fax number, like for Liz O'Brien, this particular number is a fax number, so I put it in the fax column. Okay, and if it happens to be a cell phone, I put it in the cell phone column. So if you look for Liz O'Brien, the landline number is 555-2017. That's where we have is 555-2017. But the fax number for Liz O'Brien shows up in this particular column. Since Jerry Johnson does not have a fax number, this value is null. Does not have a cell number, so that value is also null. But I hope you saw what this split has done. By having these 3 separate columns, I can now make sure that the values in any one column, not only do they all have the same format, they also conceptually represent the same thing. In other words, all these numbers are landline numbers or work numbers. All the numbers in the fax column are fax number, and all the numbers in the cell column are cell phone numbers. So all the measurements, all the values in a particular column, besides being the same format, must conceptually represent the same thing. Okay. For example, here in this first column, everything in this column is a first name. Okay. So if when I'm entering the data for this first employee, if by mistake I put Johnson over here, and then I put Jerry in the second slot over here. Now the data format is correct because I'm putting character strings which are consistent with names, but I have just violated the conceptual rule, that is, the second column, every value there should be a first name. So if I put Johnson over here, even though the text format is okay, is acceptable, I have made a mistake because it doesn't match the conceptually what that column is supposed to store. That column is supposed to store the first name, and by mistake, the name that I put in there is the last name. That's a conceptual conceptual error. Okay, so all column values must be of the same kind. That's another requirement for a table to be a relation. So here is an example of a table where all the phone numbers are they represent conceptually the same thing, but their formats are not the same. So these two numbers for Elizabeth Tran and Michael Chen, these two numbers are 10-digit numbers, but the other numbers are 7-digit numbers. So that's a violation of one of the requirements of a relation. That is, all the values in a column must have the same format, and they must also conceptually record the same thing. Okay. So the way I would fix this problem is I could make all the phone numbers to be 10-digit numbers. Okay, and then this would make the table. Then we would be consistent with one of the requirements of being a relation, which is that all values in a column should have the same format, and they should conceptually be recording the same. Uh, what should I say? They should be measuring the same conceptual thing. Okay, so all these phone numbers could be work numbers. All these phone numbers could be mobile numbers. But besides the format being the same, they should all measure the same concept, the same construct. Okay. So another requirement for a table to be a relation is that the sequence of the rows, if I reorder the rows in a table, it still remains the same. The relation is the same relation. Okay? So the order of the rows is immaterial, and the order of the columns is also immaterial. So I can order the columns in any order that I want. Typically, the primary key is put first, but that is more just for a visual convenience. From a relational database standpoint, the order of the columns is not significant, and neither is the order of the rows. Now, these two requirements, namely that the order of the rows is insignificant and the order of the columns is immaterial, it has consequences. So let's see what those consequences might be. Let's look at this first table over here. So I have 1, 2, 3, 4, 5, 6 columns, and 1, 2, 3, 4 employees really. But let's look at the phone numbers. So for Liz O'Brien, I have 555-2017 as one of the phone numbers, and 455-8096 as another phone. The only reason that I know that 455-8096 is Liz O'Brien's phone number is that it happens to be physically right next to her record. So you have this record for Liz O'Brien, and this phone number 455-8096 happens to be just adjacent to that record. So that's how I know that this number, since all these other values are null for this row, the only way I know that 455-8096 belongs to Liz O'Brien is simply because it's physically adjacent. All right. Same thing with Tom Richard. The only way that I know that 455-7098, that number belongs to Tom, is that this row is physically adjacent to Tom Richard's record. Now, at the moment, it looks fine, but since the order of rows is insignificant in a relation, I could scramble the sequence of these rows. And if I scramble the sequence, if 455-8096 is no longer adjacent to Liz O'Brien, then it would be difficult for me to make the connection that that number belongs to Liz O'Brien. So this is a consequence of the rows, the sequence of the rows being insignificant. This is an unfortunate consequence of that. How do I fix that? I fix that by filling out this particular row. So for the second row next to Liz O'Brien, I fill out the employee number, the first name, last name, and so forth. I don't leave that null. So now you can see once the row has been filled out, if I shuffle the rows, then I don't lose the fact that this number 455-8096 belongs to Liz O'Brien. By the way, notice that by filling this row out, that first condition that one of the conditions that we had for a relation that no two rows can be identical. So if I look at these two rows for Liz O'Brien, it's identical in every respect except for the last column. Okay? So in a relation, you cannot have two rows that are identical in all the columns. At least one of the columns must be different. Okay? So let's see what the consequences could be of the fact that the sequence of columns is not relevant in a relational database. You could have the columns in any order. So look at this first table over here. In the first table, and look at the column headings. I have employee number, first name, last name, department, email, and then I have the phone type and the phone number. Okay, so the only way I know, so if I just go to focus on any one phone number, 5552010, let's say I focus on this number. The only way I know that that's a phone number is because it's right next to this value phone. The only way that I know that 4558096 is a fax number is because this number happens to be adjacent to the value fax. Okay. Now, if I were to shuffle the columns, remember we said that the order of columns is insignificant. Suppose I shuffle the columns so that this phone number now becomes the third column over here. Then it would be very difficult for me. It's not immediately obvious that I would associate a phone number with fax, or this particular number with cell. Okay. So the way to fix this problem is to create these separate columns. So since I have three different kinds of phones, so I have one column called phone number, another column called fax number, and another column called cell number, and I put the values accordingly in those three columns. Okay. Now you can understand, if I shuffle the columns, if I shuffle this particular, if I shuffle this guy, if I moved it over here, there would be no difficulty in my deducing that 4558096 is a fax number, just from the heading of the column, right? Same thing with this one, this 4557098. The fact that it's a cell phone number is now pretty evident because I can figure that out from the heading of the column. I couldn't do that with the setup that we had here. In this first setup, the way I infer that 4558096 is a fax number is because of its adjacency to the value fax. I don't have to worry about that anymore by modifying the structure of the table to look like this. Okay. So essentially what we're saying is, unless you're careful, the simple statement that the order of rows doesn't matter, the order of columns doesn't matter, unless you're careful in the way you record your data and structure your database, you can run into some complication and run into some difficulties. Okay. Okay. So what have we gone over in this particular lesson? We are introducing the concept of normalization. We haven't yet gotten to normalization. So the point that I made was normalization is a rigorous way of doing something that we informally did in the very first class. That is, we looked at a table, we put everything into one table, and then we examined and said, hey, that's some undesirable properties. And to sort of mitigate against those undesirable properties, we informally identified themes, and we decomposed this one table into multiple themes, and then connected the theme through parent-child relationship and so forth. Okay, but we did all of that informally by eyeballing that one table and trying to find groups of columns that go together. Normalization, which we will begin with our next video, normalization is a rigorous process for examining a relation, deciding whether or not it has desirable properties, and if it doesn't, to go through a formal process of decomposition that gets the relations into a desirable shape. That's what normalization is about. And in order to set that stage, we went back and revisited the concept of a relational of a relation that we had introduced informally in lesson 2. So in lesson 2, we had a quick discussion of what is a relational model, what are its basic components, because that affected the data modeling process. And now we are coming back, and we just took a much more detailed look at what constitutes a relation, what are the properties that makes a table a relation, and what are the consequences of those properties. What consequences does it have in terms of our structure in setting up the relation, and in interpreting the values that are stored in the relation.